Hello and a warm welcome back. Today on the bench is an amplifier, 807 push pull 25 watt-ish amplifier with my my gain stage on the front. Sorry I've not posted for a while. I've not been very well, and I got to the point with the 2C34 amplifier where I sort of got a bit stuck and a bit fed up with it. And so when Ian, my friend, asked me to have a look at this amp which he'd already built in his own inimitable style, I said yeah, I'd do that. And I've just sort of been, basically I had to pull out, unfortunately, most of what he'd done because it was a bit, I mean, it might have worked, but it wasn't the best, let's put it that way. And Ian knew that, I think. So anyway, let's have a closer look. Okie dokie. So what we've got here, we've got a 6H8C dual triode, which is similar to a 6SN7 ECC 82 type sort of valve. Basically got our two input voltage gain stages for the left and right channel going in there. And moving over this way, we've got a long tail pair, which is another 6H8C with a constant current source, constant current sink on the cathode there, 247k anode resistors, blah de blah de blah. That then goes into our two 807s here. I powered it up, tested the DC conditions. They're about right. I had to make a slight change over here on one of the resistors that goes to the decoupling there. I had to change its value, and then there's a few minor sort of tweaks. The heater voltage is 7 volts, which is too much, so like Ian has done here, got a couple of resistors to drop that. I'll have to do the same on that. And that's the heater that feeds the input stage. I powered it up as mentioned, checked all the DC readings, they're okay, happy with those, and I also put an AC signal in. I got about 26 watts out of it with 500 millivolt input voltage. And then what I did, I didn't do like a whole load of testing. I just did a quick sort of frequency test, and it had a really good frequency response actually. It was basically flat from about 20 hertz to about 50 kilohertz, which ain't bad. Or it might have even been more, 60 kilohertz. I was quite surprised actually. So what I did then was, with basic tests, was we've got a 20k 10 turn pot, fed some feedback in, adjusted that until I sort of got, like a dropping of the total harmonic distortion, and about right. And so then I fitted a resistor, just a normal resistor in, put a sine wave in, a square wave in, and then use my capacitance, what do you call it? Fucking hell, what's it called? The capacitance box. It just basically, you can set the capacitor, the feedback capacitor. And so I determined that that was about right with 2200 picofarads, or 2N2. So what we'll do now, we'll bung a sine wave in, have a look at each channel, and then we'll bung a square wave in and have a look, eh? Quick test. So this is reading the left channel. This is the one with feedback on. The other one hasn't got feedback. We've got a RMS of 2.6 volts, RMS should I say, and 0.26 THD. hoping you can see that. So there's the sine wave of the left channel. If we have a look at the right channel, and on the right channel we've got, I've set it for 2.6 volts RMS out and a THD of 1.9%. so that feedback, you know, the negative feedback really cleans it up. Right, let's bung in next a square wave on this channel and I'll show you the result. Right, to you. I'm just showing you the top of the square wave now into the left channel. This is the one which is open loop, no negative feedback. And as you can see, we've got some overshoot, a little bit of instability, and there's thickness on the top which is also indicative of instability. And we've got some low frequency roll off. Just expand that a bit. See there on the bottom. So what I did when I selected the capacitor and feedback resistor, I tried to get rid of that, and so essentially, I mean, we're limiting the frequency response of the amplifier. That's just a 1 kHz sine wave. Let me pop in 10 kHz sine wave. Right, let's zoom you back a bit, try and get that. So as you can see, that's sort of telling us the same thing, bit of overshoot, bit of instability, but I would have expected that. 807s are designed as transmitting valves, and so they can have a propensity to self-oscillate. Right, so that's our right channel. Let's have a look at the left channel with the feedback applied. So it's a 1 kHz sine wave going in, fills most of the screen. Frequency 100 Hertz. And as you can see, we've got no loss of signal, still a good sine wave. 20 Hertz. And as you can see, no loss of signal at all. So basically the 0 dB loss or attenuation from 1K down to 20 Hertz. That's 10 kilohertz, 20 kilohertz, and that's 50 kilohertz. And we've got a little bit of attenuation, but it's not 3 dB. Let's see where the 3 dB is. Frequency 60 kilohertz. Fucking hell. Frequency 70. Right, are we about half yet? No, it's still at 70 kilohertz. It's still not 3 dB. Frequency 80 kilohertz. Right, and that's about 3 dB. It's still not 3 dB down, look. It's still over half, you know, over halfway, peak to peak, which is damn good. Let's see where it is. Frequency 90 kilohertz. Well, this is amazing. Oops. Frequency 100 kilohertz. Wow. That I have, all the amps I've built, I've never seen frequency response that good using these. I mean, they're not really expensive output transformers. They're just primary winding, sort of 100 quid output transformers. 6K6 primary impedance. Yeah, and as you can see, that's brilliant. So basically, it's got a flat frequency response from about 20 Hertz to about 80 kilohertz. Frequency 80 kilohertz. What am I talking about? Right, well now, frequency 50 kilohertz. Right. Okay, that's wrong then, what I just said. Frequency. Right, I'm sure on the way up we didn't have any attenuation. Well, that's still at 40k, it's still bloody good. Let's have a look at the other channel. So this is the left channel and this is the one without any negative feedback, so this is open loop. Try and adjust that down a bit. Right, so that's what, 40k. Right, that's gone down there. That's about, well, it's more than 3 dB down at 60k. So the one with negative feedback has better frequency response. So yeah, not bad. Right, well, those tests that I just did there was a bit crap frequency, so let's put some figures on the thing. So what we on now, we're on the left hand side. So we're measuring the left hand channel. So this is noise. Got 101 Hertz, which means that's rectified mains probably, and we've got 5.4 millivolts, which isn't too bad. Let me just have a look at the other channel, and about the same on the other channel. Right, okay, just replug me doodah in. Right, now let's try again. Right, so we know what a noise figure is. Know what a noise figure is. Next, let's do a maximum output test. One kilohertz sine wave. Got 14 volts, still not clipping. Okay, it's just clipping there, look. That's with a 1.5 volt input, 1.5 volts RMS input, and we have 14.63 volts, which is 26 watts, which ain't bad, is it? Right, let's just go back to there. Let's have a look at the THD, and that ain't bad. 26 watts at, let's call that 0.2 volts percent total harmonic distortion at 1 kilohertz. Let's see what that's like at 100 hertz. Right, it's just gone up a bit. And 20 kilohertz. Ooh, that isn't good. Look, we've got, right, that's probably because it's clipping. Just knock that down a bit. Yeah, 1.6%. So yeah, I'm not really 100% happy with the frequency, with the distortion, high frequency. Right, now then, let's have a look at the frequency response. So first we got it. We need set a mid frequency. So to measure frequency response with this HP893B, or however way you do it, set your frequency to 1 kilohertz. That's the middle frequency, right? And then get a figure, say about 3-4 volts, 4.2 volts. Then we've got to set it to dB. Let's find out once and for all. dB, that's 0 dB. Okie doke. So now we go down to 20 hertz, and that's giving us our frequency response in decibels, and it is 0.06%. No, sorry, 0.06 decibels down. Let's go to 20 kilohertz, which is normal, and that's minus 0.44 dB down at 20. Let's just go up to 40, save mucking about. At 40 kilohertz it's still only 1.6. Oh, you bugger, I can hear that. I mean, I don't know, I shouldn't be able to, but I can. Right, 60, it's too far. Yeah, so that's at 50 kilohertz, it's down 2.5 dB. Let me just go back. Which I think is quite good. Right, so now we've got some figures. I hope I can, well, I've got it on video and I, so I don't have to remember it. Right, so that's good. The square wave response, it isn't brilliant. I've done testing it up the yin yang. Let me just check the other channel, make sure we're getting the same sort of thing. So this is now the left channel. Ooh, right, about 20 kilohertz. Frequency 1 kilohertz. .9, right, clip in there, look. So we've got about 26 watts out as well, which ain't bad. Check the THD, and again it's at about 0.23%, and that's okay. Right, let us take it off the bench, take it in the other room, and this is what it's all about. It doesn't matter what the frick it tests like, we have to make sure it sounds alright. I mean, you know, if it don't sound alright, then, well, we've got to go back to the drawing board and make some changes. Right, let's get a go.
Now here comes our special request to each and every one, especially those my brethren who forget where they are coming from, you know. This song is called Roots and Culture.
Yeah, well, it can produce a bass alright, and it's got a nice top end and all, and I think that's about all there is to say. I think, as usual, I've talked too long, so I'll shut up. Thank you all very much for watching. Take care of yourselves. Ta-da for now.